Good afternoon. My name is Anthony Castillo, and we are the 2020-2021 two-wheel obstacle avoidance robot team, sponsored by Raytheon Technologies. Our team consists of Cheung and Wyatt Luong, who were both responsible for the research and development of the wireless controller, and Taylor Hemwall, who was responsible for the troubleshooting and testing of the balancing function. Our faculty advisor is Bob Dempster, and our Raytheon liaison is Dr. John T. Jacobs. First, I want to talk to you about the introduction and the scope of the project and requirements. This is an ongoing project. The first objective we have is for the self-balancing function. The method that we chose to use to do this is the IMU. It's using an IMU, or an initial measurement unit, and a PID, proportional, integral, and derivative controller, to control the inherently unstable system. Our second objective is the obstacle avoidance function. We plan to do this through using an ultrasonic sensor using ultrasonic sensors to detect objects within 1 foot of the robot. And our third objective is wireless control of the robot. And our method is using an RF radio frequency transceiver to give wireless commands to the robot from a joystick. The objective of the two-wheel obstacle avoidance robot team is to have the robot balance on 2 wheels while being controlled wirelessly and avoid objects autonomously. The robot shall be capable of balancing continuously for 15 minutes, shall accept and execute movement commands from a wireless controller, and shall autonomously avoid obstacles within 1 foot of the robot.
Thank you, Anthony. Now I will be talking about the project overview. Here is our current design. We have a 2-level robot. Here we have our front view of the robot. We see there are 3 ultrasonic sensors on the top platform, a LiPo battery on the lower platform. Stepper motors and wheels are below that. Here from the back view, we can see the main microcontroller, P6, IMU, motor drivers, and a buck and boost converters. We upgraded the battery to have a greater power capacity so that it could provide additional power headroom for the robot to run for longer durations. There is only 3 ultrasonic sensors showing, but there will be 5 of them that will be implemented onto this robot. Next slide, please. Here is the system architecture. As there are 3 primary functions our robot needs to handle, they are balancing, wireless control, and obstacle avoidance. We will use software interrupts to execute these 3 tasks in order of the priorities to ensure a functional transition between each functions. As for the system architecture, we want to ensure that different functions of the robot can communicate with each other. Here we have the robot sensors, which are the sensors on the robot. They are the IMU and RF receiver. They provide inputs to the software, which they allow all functions to achieve their tasks. The balancing will be active at all times. And the second priority is the obstacle avoidance feature, because we do not want the users to have the power to crash the robot by accidents. And the last priority is the wireless control. As long as the robot is balancing and it is not hitting anything, then users are allowed to move it to any direction they want. The output coming from the software, which are then provide the motor drivers commands for the robot in order to achieve the 3 functions that we want the robot to achieve. Next slide, please. Here we have the overall software flowchart. As mentioned earlier, there are 3 primary tasks we wanted to achieve with the robot. So in order for the robot to perform each of the 3 functions, the balancing, obstacle avoidance, and control the robot wirelessly, we will use software interrupts. With this, it allows our main microcontroller, P6, to choose which tasks to execute first, based on their priority level. We have set the first priority to be balancing, because it is the most important functions. The robot must be able to balance on its own on 2 wheels before it can perform other tasks. The second priority is obstacle avoidance, because the robot needs to go around the objects on its own without the user's input interfering with this process. And the last priority is executing wireless commands if the robot does not need to balance or avoid obstacles. Next slide, please. On these slides, we have the electrical block diagrams. Here is the overview of our entire systems. In our diagrams, here are teams 2020 highlighted in orange. So here basically it shows what components our robot consists of. The main microcontroller for our project is PSOC6. And it basically handles everything because everything will be connected to it. All of our 5 ultrasonic sensors are used for obstacle avoidance, and they'll be also connected to the PSOC6. One of the recent additions to our robot systems that we have just finished building it is the remote wireless controller. And now it's using the PSOC5 secondary microcontrollers and a 3.7 LiPo battery and RF transmitter. And the wireless controller will be wirelessly interfaced with the RF receiver on the PSOC6 on the robot. So here on the diagram, we will also have inertial measurement unit, IMU, that will be used for balancing. And it's like a combination of a gyroscope and an accelerometer. We installed a new 11.1 LiPo battery this year, and now it connects with the buck and boost converters, which they reduce and increase voltage respectively in the system according to different components specifications. The battery is used to power the motor drivers and the PSOC6. So ultimately here, the PSOC6 produces commands to the left and right motor drivers, which provide the instructions to the left and right motors. Next slide, please. So here is a battery trade study. We have decided to go purchase a new LiPo battery, the Go Back battery, for our systems. We chose this one out of the other available battery options in the market because it could provide 42% headroom at the lowest cost, and it could allow a robot to run for longer durations. Next slide, please.
All right, thank you, Ken. And now I'd like to talk a little about how our robot balances. So the diagram in the top right corner shows how a robot balances on 2 wheels. This means that it is unstable in the theta direction, and it must have a control system to stop it from tipping and falling over. The inertial measurement unit, known as the IMU, on board takes the measurements that are needed by this control system. The IMU is a combination of a gyroscope, which measures the angle that the robot is at, and an accelerometer, which measures the angular acceleration. These measurements are all taken in the roll, pitch, and yaw directions and output to the PSOC6 microcontroller. The software control system on the microcontroller tells the robot which direction to move based on the roll angle and how quickly to move based on the roll acceleration. Next slide, please. Our robot behaves like an inverted pendulum, which is inherently unstable, whereas a regular pendulum is inherently stable. This again means that it needs a control system. For an inverted pendulum, the pivot must be moved below the bob in order to balance, which in the case of our robot means moving the bottom platform with the wheels underneath the top platform that holds the microcontroller. Next slide, please. The control system we're using is known as a PID controller, which stands for proportional, integral, and derivative. What it does is it compares a reference value set by the user, in our case, the robot being upright and at 0 degrees, with the current output that's measured by the IMU. The difference between these two values is known as the error signal, which is then processed by the PID controller and generates a control signal that helps the robot to balance. The proportional term is based on the current error and helps the robot to balance more quickly. The integral term is based on the sum of the previous errors and helps reduce the steady state error of the robot balancing. The derivative term is based on the current rate of change and helps to reduce unnecessary oscillations while the robot is balancing. And the control signal is made up of all these terms. Next slide. The PID values necessary to make the robot balance were obtained by the first year's team just by random guessing and experimenting with different numbers. The second year's team improved upon these values by extensive trial and error and observation. Our team wanted to take a more systematic approach to this, so we wrote a MATLAB script that was capable of generating these values automatically, using the weights of the top and bottom platforms of our robot. The expression on the bottom right will show how these PID values are summed together and generate a control signal, with S being the complex frequency variable representing sigma and j omega. Next slide, please. The steps taken by our software function to balance the robot are as follows. First, the IMU is initialized. Second, the user holds the robot upright in a fixed position during the calibration process. And next, the calibration process takes 2,000 measurements for the gyroscope and accelerometer roll, pitch, and yaw values and averages them, then uses these measurements to generate offsets, which account for the IMU's physical alignment on the robot, which may not match gravity. Once the calibration process is over, the robot will balance on its own using the PID controller that will generate movement commands to make it balance. Next slide.
Thank you, Taylor. Now I want to talk about how the robot avoid obstacles. So two functions must work before implementing the obstacle avoidance function into the robot. The first is the ability to detect obstacles. And the objective of this task is to detect obstacles within 1 foot in front or on the right or left side of the robot. The other is the ability to avoid obstacles. The objective for this task is to avoid detected obstacles in front and on the right or left side of the robot. First is obstacle detection. And we are accomplishing this through using ultrasonic sensors. Ultrasonic sensors are programmed to send out a small voltage to the trig or trigger pin that will then trigger the sensor to send out a 10 microsecond 8-cycle sonar pulse signal that is then reflected back from the object in front of it. Once the signal returns to the sensor, it is flagged with the received echo signal, and the time between the trig and echo signals can then be calculated and be used to find the distance of the object as shown in the equations to the bottom right. Next is obstacle avoidance. And we chose to accomplish this through this method. The robot will default to turning right when an obstacle is detected straight ahead or to its left. It will then continue to move forward while checking for obstacles to the left or right side of the ultrasonic sensors. Finally, it will turn back to the starting position when the obstacle is cleared. The opposite commands will execute if an object is detected on its right side ultrasonic sensor. During the obstacle avoidance loop, the robot will not process any commands from the remote controller until the obstacle avoidance is complete. The robot will give control back to the balancing function after each turn is completed. Now I'm going to talk about the flow chart. The robot, first the robot checks if an object is in front of it. Then if an object is detected, the obstacle avoidance begins automatically. The robot turns left or right based on the shortest path, and then maneuvers around the obstacle. Then after that, the robot returns control to the user. This is the ultrasonic sensor accuracy test results, and these tests were done using the setup on the bottom left picture, and they show the numbers that we were supposed to be getting 0.5, 1, 1.5, and 2, and shows the sensors values, or the values coming out of the sensors. As you can see, the numbers are a little off. However, the numbers are consistent. So all we would need to correct this is a calibration curve. This is the ultrasonic sensor synchronization test results. We were able to synchronize up to 4 sensors at once. We did this by creating an infinite loop and trigger each sensor consecutively with a 30 millisecond delay in between sensors to give the software program time to complete its function.
Thank you, Anthony. Now I'll be talking about the wireless control function. Next slide. So one of the requirements we want this robot to achieve is to receive a control signal from the remote controller, which controls the robot's movement according to the users. And in order for these wireless communications to be executed, An SPI or serial peripheral interface is necessary in order for the transmitter and the receiver to send and receive data respectively. And as seen on the right figure, the controller design consists of a PSOC 5 LP board, an NRF transmitter module, a 3.3 volt buck converter chip, a 3.7 volt LiPo battery, an Adafruit boost converter, and a thumbstick. And so far, for the wireless function, it has been confirmed to be working properly through numerous experiments, such as the range testing, which is confirmed to be working since transmitter can send consistent data to the receiver within the range of 50 feet, and the power measurement, which is confirmed to be working for at least an hour, which exceeds the 15-minute requirement. Next slide. So for the joystick function, we expect the robot to move according by the user's joystick position when they toggle. And for the software program, it will continuously monitor if the user touches the joystick at any moment while the robot is balancing simultaneously. And if you look on the right, it will show how the joystick could be toggled in X and Y position at 4 possible directions of the robot's movement. And there's an exception time where the wireless control function will be rendered inactive when the obstacle avoidance function is activated. Next slide. And now I'll be talking about the conclusion for this presentation. Next slide. So for implementation, the following code has been created and needs implementation, such as the obstacle detection and the wireless control function, which needs to be integrated onto the robot. And as for hardware implementation, it needs 2 more ultrasonic sensors. And as for wireless controller, it needs a 3D printed case in order to protect the components from damages. Next slide. So for the future teams testing, they'll need to test on the obstacle avoidance function, the wireless function when it's integrated on the robot, ensure that the voltage ratings are correct in order for the motor drivers and the stepper motors to be working properly, and also for the robot to be balancing on 2 wheels. And as for improvement in the future team will have to modify the existing software in order to handle the inputs from 2 more ultrasonic sensors. Then they'll use the simulated PID values as a starting point in order to test the robot balancing function. And then they'll measure the execution time for each function with a timer, and then modify the software for the robot to prioritize all 3 functions using a software interrupt. Next slide. So for this team overall, our accomplishments are the following. The wireless controller is fully functional as verified through experimental trials, and we use the 4 ultrasonic sensors to accurately detect an object in front of the sensors simultaneously. And lastly, we replaced the old LiPo battery with a new LiPo battery in order to increase the power headroom. And for this conclusion, we have made progress on the battery choices, obstacle avoidance, the IMU signal, and the wireless control functions. Next slide. Thank you for listening, and hopefully you find our presentation to be informative on the 2-wheel obstacle avoidance robot. Thank you.